Thanksgiving, so thank you all for coming. It's nice not to be talking to a completely empty room. I'll start with some corrections for a couple of minutes, and I want to say I haven't been sort of advertising the best application of this stuff, so I want to briefly advertise that in case you are interested. And then I will spend most of the lecture talking about how do you actually compute square 2. And what do you need if you wanted just the operation square 2 for your favorite chain complex? So that should actually, it's going to be a little bit tedious, but also a little bit, maybe a little bit interesting. So corrections. 1, today's lecture is today. I think I said it was a week from today. So you're here, you've figured that out. OK, that was sort of terrible. 2, I said it's squeeze knots. So there's this paper about squeeze knots by Ida and Suzuki. And I completely mischaracterized the paper. Not completely, somewhat mischaracterized it. They prove an infinite family are not squeezed. They don't just do the pretzel that's in the title, P of 4 minus 3, 5. So the paper's like P of 4 minus 3, 5 is not squeezed, is what it's called. So they do an infinite family. So that was one thing I said wrong. And I also said that the techniques I was explaining don't prove the result. The techniques I'm explaining do prove that this knot and the first few others in their infinite family are not squeezed. So actually, this techniques work for that. It's just nobody had, I think, checked. Awesome. It would be interesting to know if the whole infinite family could be gotten with these techniques. You would need some idea for doing that computation. So there's like a little project somebody could do if somebody was bored. OK, check. Different sort of application. So the nicest results using the Khovanov stable homotopy type due first to Stoffig and Zhang. Oh, as always, references are on the web page. Is to knots with symmetries. So knots with symmetries. For example, if you have some sort of a rotational symmetry, you can consider a knot, and you can consider the quotient, like K mod Z3, which is the unknot in this case. And you could ask for a relationship between the Khovanov homology here and the Khovanov homology there. And so Stoffig and Zhang proved more or less that the Khovanov space of the quotient K mod ZP is the fixed set of ZP action on the Khovanov space of K. It's like, this is not true at all, but it's like this is some space of fields, and the space of fields downstairs give you equivariant fields upstairs, so they're the fixed set under a Z mod P action. Doesn't make any actual sense, but that's how this and Hegardt-Fleur and symplectic Fleur monopole, a bunch of other theories, similar theories, all sort of behave. And so this gives you conditions on homology by applying classical algebraic topology. And the reason you need the space is that, like, group actions on chain complexes don't really have fixed sets. Group actions on chain complexes don't really have fixed sets. There's not a sort of appropriate notion, like a well-behaved notion there. So fine. So the existence of the space and then some properties give you something about Khovanov homology. It gives you a spectral sequence, like a rank inequality. This is bigger than that. And then we had some other toy applications that I put some links to in the online. And this had some actual applications, like proving that knot Fleur homology detects the 2-5 torus knot. OK, that was that. Oh, I mean, so what's the intuition? It's like, suppose, so I don't know. it was some attempt to give, like what is, if you wanted something like this in monopole Floer homology, you would be talking about like spinors upstairs for k versus spinors on the quotient. And so there's some sort of fields or something that you're studying for your invariant, and there's a group, like the fields downstairs or the fixed set of the fields upstairs. But there's no field, like these fields I'm imagining don't actually exist. Suppose this was the homology of something like K that came from physics, is what I'm saying.
So you actually get a map on, like Z-mod P action on the spectrum.
You do. You do, yeah. Just by doing the construction that we gave carefully. That's a good question. Yeah, this actually works. The intuition is just nonsense. Yeah. More questions? Okay, so our goal is I want to consider, so let's, for the moment, I'm going to write x, say this is the like xkh of k. This is a CW complex. And I want to compute the Steenrod square. So we have hn plus 2 of x f2 hn of x f2. And I'm trying to compute this first interesting operation, the first new operation, square 2. So first I'm going to reduce this a little bit. So I've got an inclusion from the n skeleton of, or say the n plus 2 skeleton of x includes into x. So it's my n plus 2 skeleton of this thing. And that gives me a map on cohomology, the other direction. Good job, me. So this goes to hn plus 2 of x f2. And this goes to n plus 2, sorry, of x, good job, x n plus 2 f2, and hn plus 2 of x n plus 2 f2. And I still have a Steenrod square there, and the Steenrod square is natural, so that commutes. This is an isomorphism because this only depends on the stuff around grading n. Yeah. It is. Thank you. Good. Any other typos? There will be. I think maybe okay so far. And this is injective. Because like this is the kernel of this to the hn, the cn plus 3. And now I also could look at, let's do this one first, hn of x n plus 2 mod x n minus 1. So we have a quotient map the other direction, so this maps there. And hn plus 2 of x n plus 2 mod x n minus 1. I've got a square 2 there. OK, now this arrow is an isomorphism because I'm only playing with cells that are way away from n plus 2. And this one is a surjection. The upshot of this is that if I understand, so upshot, if I compute this square 2, I've computed that one. Because you take the generator you want to square, it comes from something over here. Square it. Wherever it went to had to come from something here, and that thing was unique. Right? Because this was injective. So the surjective and injective is exactly what you need for this to determine it. So I may as well assume that x only has cells in dimension n, n plus 1, and n plus 2. So can assume x has cells only in dimension n, n plus 1, n plus 2. And now how are we building xkh? we had this functor from the cube, maybe I called it F, from the cube to the Burnside category. This was this category of sets and matrices of sets and bijections of matrices of bijections. And let's go a step. Sorry, let's come to that in a sec. Let's come to that in a sec. Sorry. So how do we build this thing? Well, the previous step was we had a bunch of spheres. So we had a diagram of spheres, 2 to the n to spaces, sending a vertex v to the wedge sum over the Khovanov generators over v of a sphere. That's, yeah, let's reverse which n is which. That'll be 2 to the capital N. This will be s little n. That matches there. So, and then we took some sort of mapping cone, iterated mapping cone. And this truncation tells me we can forget all of the spaces for gradient of v not between n plus 1 and n plus 2. We'll call this a D. Okay, sorry. So there's some suspension and desuspension that's supposed to happen, and I'm trying to suppress it, and it means that my gradings are slightly messed up. So like, there's like a sigma to the minus d at the end, and anyway, the d's and the n's are going to be slightly off. Okay, so what this thing now looks like is I have a piece of a cube. So before I had, I don't know, a cube. Can I draw a cube? That's not so good, but that's sort of cubish. It's cubish. Okay, we had a piece of a cube. So we had a cube, and now I'm truncating near some 3 levels in my cube. Well, it's like a hypercube. So what this diagram now looks like is I've got a wedge of spheres, some at a bunch of vertices here, and some other wedge. So this is like absolute value of v equals n, a bunch of other wedges of spheres, where absolute value of v is n plus 1, and a bunch of other wedges of spheres where absolute value of v is n plus 2. And some maps. Okay, so it's not just a square. I've taken a big dimensional cube and I've sliced off in 3 consecutive gradings of that big dimensional cube. Fiona.
Are the numbers there just for illustrative purposes?
Yes. The numbers are completely just for illustrative purposes. And in fact, these numbers don't, I think, appear for any dimension of cube. So sad. Yeah. Okay, but outside here, I've just got, everything out, all the absolute value of v equals n minus 1 is just going, say, to a point, and everything absolute value of v bigger than n plus 2 is going to a point. Just some sort of trivial space. So I just truncated over here. In terms of the Burnside functor, that means that, like, f of truncate, we just set f of v is empty set if the gradient of v is not in n plus 1, n plus 2. So just forget all of the data outside the range. We're looking at all the Khovanov generators out there. We're only interested in the ones between n and n plus 2, and we can focus on that because of that diagram. And now, so the next step I want to do is I'm going to collapse this from being a piece of a cube to just a short linear diagram. So I'm just going to take the wedge sum of the things I had at absolute value of v equals n. So in this case, I drew that as 2 in my nonsense picture. And here, SD, SD, SD. These v's are like indicating it's a wedge sum of a bunch of spheres. And here, wedge sum of SDs, a wedge sum of SDs. Okay. So this is supposed to be the analog of taking the total complex. I'll come back in a minute to sort of, well, I'll say a little bit about how you go from here to there. Okay. Maybe I should say so. I mean, how do I go from here to there? Some of these edges have a sign, like some of these come with a minus sign. I don't know where well, specifically not there, but like some of them come with a minus sign so that all the faces anti-commute. And if I had a minus sign, you just compose with the reflection. So compose this map with a reflection and just add up all the maps. So great. So let's call this, I'm going to call this a short chain complex of spaces. Okay, so a short chain complex of spaces looks like A, B to C, nothing outside that. Where each of these is, say, a wedge of spheres. I lost the property that the squares commute. So what was the fact that the faces commute up to homotopy? And that's that this composition, let's call this, say, FG, F circle G is now null homotopic. Originally it commutes. Then this commuted, and then there's some signs in the taking total complex. But the signs I put on are just the same, just exactly the usual Khovanov signs. Yeah, so it commuted, and then I'm putting on signs so it anti-commutes. Then the fact that this square anti-commutes means that this map plus that map is null homotopic. And which this square anti-commutes means this map plus that map is null homotopic. And in fact, I didn't just know that it homotopy commuted, I had the homotopy as part of the data. So in this short chain complex, this homotopy, let's give it a color. How about red? This homotopy, this is a null homotopy of F circle G as part of the data. So I have A, B, C, and I have a null homotopy here. That is, what should a chain complex be? It's like a sequence of abelian groups so that d squared is 0. And here d squared is 0, but in fact, I have the reason it's 0 is part of the data, the thing certifying that it's 0 is part of the data. So in particular, this gives me what I'll call a short chain complex of abelian groups by, you just take Cn, what's n? D, cellular everywhere. So this wedge sum of spheres just turns into a direct sum of z's when I take C and CD cellular, and this is another direct sum of z's. And the fact that the composition was null homotopic means that d squared is 0. So a short chain complex of abelian groups is just, z to the alpha, z to the beta, z to the gamma, so that this is 0. You could think about what it means to have a longer chain complex of spaces, and there's a perfectly good answer which boils down to basically being a CW complex. But it's a sort of funny way of thinking about a CW complex. So it's a puzzle to think about later. What would you mean by a longer chain complex of of spaces? But we don't need that because we reduce to this. I should have meant to say at the beginning. So the sketch I'm going to explain for computing square 2, I'm going to follow some papers of Jones, Lipshitz, and Orson-Schutz for computing square 2. There's just you can also just write down a formula. But the formula is, I think, uninsightful, whereas this will, I think, maybe be useful conceivably to somebody. This way, which I'm explaining, is I think also how NotJob works, which is the best computer program for computing the stuff at the moment. So it's also efficient is too strong, but it's as efficient as we've got. References are still on the web page. OK, so how did we get this short chain complex of abelian groups, sorry, not of abelian groups, of spaces, short chain complex of spaces from, let's say, the Burnside category. So I want to go back to some more combinatorial data than that diagram. That diagram, I have to specify a bunch of maps between spheres and some null homotopy, and that's not on its nose combinatorial information. So I want to go back to where did that come from for us. It's going to be helpful. So we had, well, great. So we had, OK, 2 to the n went to the Burnside category, and so we replaced, so f of v was a set, and that turned into the wedge sum over a in f of v of SD. So that was what happened on vertices. That's OK. For morphisms, so if for v to w, an edge, we had this f of v to w was a matrix of sets. So this was an f of w by f of v matrix of sets. Yuck. And now we embedded them, f of vw, f of v to w, the part over a comma b, b comma a, into the sphere corresponding to a. So I had this sphere SDA. I embedded this set in it, and then we did a Pontryagin and Tom type collapse thing. So I took a neighborhood. So this gave me SDA goes to a neighborhood of f of VW BA mod boundary. So this collapsed onto a wedge sum of 3 spheres. And then that went to the sphere for B. OK. I want to be able to take this total complex where I put in these signs, the Khovanov signs. How am I going to do that? Well, I need to be able to compose. These maps are always the identity map on each fact. I mean, it's some wedge sum of identity maps. So it's full pinch, and then I do a bunch of identity maps. I need to have some orientation reversing ones also. So let's generalize B. Instead of, so f of v is still a set. But the morphisms f of v to w, this is going to be a matrix of, what are the entries though? A matrix of framed zero manifolds. That's, I mean, of course, it's framed compact zero manifolds. OK, a compact zero manifold is just a finite number of points. Right? So that's not changed. All I've done is I've added a choice of a sign to it. So think of the points at some eventually are going to live somewhere, and think of them as having, some basis for the ambient space. So framed means with trivialization of normal bundle. And the sign is that, again, it's going to be embedded. I'll say that. I'll spell that in a minute. And is that the positively oriented or negatively oriented is the sign. And now the two morphisms were bijections of sets. So if I have a set here and another set here, and I have a bijection between them, whoops, like, I don't know, there's a bijection between them, that's the same as having a, well, that's a special case of having a one manifold with boundary connecting the things, where the boundary is this one, disjoint union that one. Okay, and I should not forget that now some of my points can be have negative signs, so plus a framing of this one manifold. Okay, so instead of bijections, I now have framed one manifolds with boundary.
Sorry, I think you just explained this, but what's framing?
Yeah, what is a framing? I said I'm about to explain that. A framing is a trivialization of its stable normal bundle. But I'm going to say that very concretely in a few seconds. So this was actually motivation. That's why. So don't panic. So I'm going to now say this a little bit more precisely. So this data that I needed in order to construct my diagram here, diagram there, is a framed one flow category. So I wrote it as F. That's a mathcal F, in case we're keeping track. Consists of finite sets Fn, Fn plus 1, and Fn plus 2 of objects, if you think it's a category, or critical points, or generators. For every pair A in Fn and B in Fn plus 1, a framed zero manifold f of BA. And also for every b in Fn plus 2, sorry, in Fn plus 1 and c in Fn plus 2, a frame zero manifold f of CB. And then for every A in, I know I still haven't told you what framed means. I'm coming. It's coming. Don't worry. I promise. For every A in Fn and C in Fn plus 2, a framed one manifold f of CA with the boundary of f of C as, don't be ridiculous, new page. Look how much worse that is. With f boundary f of CA is the disjoint union over B of f of CB times f of BA. Okay, and now what is the frame? So let me, so here, say f of BA is embedded into RD, which maybe we think of as sitting aside SD. And the framing is a trivialization of its normal bundle. Similarly, f of CB is embedded into RD. So that tells me that then f of CB times f of BA is embedded into R2D. And f of CA is embedded into R2D cross the interval 0 infinity with boundary f of CA is f of disjoint union f of CB times f of BA times 0. So let me put on an example that will be my example I play with for the rest of the talk. I took advantage of your absence to define framing. What was I saying? So, for example, I'm going to consider the following framed flow category. So first I'm just going to write down a chain complex for you. So here's a not very exciting chain complex. Let me give you the coefficients. So 1, 1, 1, 1, 1, minus 1, minus 1, 1. Yes? No, that's a great question. They absolutely can be empty. Yeah, great question. And so here, I'm going to have a framed one flow category F. Its objects are, so Fn is, the set of A1, A2. Fn plus 1 is the set of B1, B2. Fn plus 2 is the set of C1, C2. And now let's say that f of ci bi is a single point, and f of bi ai is a single point. And again, I'm defining an example, so there's nothing to check. Well, there's not yet. There's about to be. F of ci ai is an interval. I just, said by fiat. And now these all have to have framings. So they embedded, so the framings look like the following. No, too bad. Framings. Keep going. So here is, say, f of C1B1 and f of C1B2. This is R. D is 1, so I can draw what I'm drawing on the board. Here's, say, f of B1A1, f of B2A1. And now there are framings, so let's frame them. These are both supposed to be framed positively. Why? Because I wrote +1 up there, so I want to get that underlying chain complex. This one, B1A1, was positive, and B2A1 was negative. And now f of, here's f of, well, here's nothing. Here's RD cross RD cross 0 infinity. My coordinates today are x, y, z. This is f of C1B1 times f of B1A1, and this is f of C1B2 times f of B2A1. Here's f of C1A1. And we had framings that looked like that, and this. And the framing of this one manifold is just a family of vector fields that, I don't know, maybe it goes around the back over there and connects this one to that one, and let's hope it somehow wanders around to be over here. Crash. Good? This is what the data looks like. Questions? Okay. There aren't very many framings for a one manifold, so or a zero manifold. So after choosing some conventions, that is, some global choices, conventions, a framing of the zero manifold is just the same as choosing a sign for each point. That is, if I gave you these arrows, I could just as well do this one is plus and that one is minus, and you could reconstruct the arrows. Now, if this was bigger dimensional, I'd have to say, well, this is plus means it's a positive copy of this specific basis, and that's negative means it's, it's a copy of this other specific basis. Yes, Fiona.
Maybe I'm doing some of the thing that I'm sort of getting is that I don't know how I would get them to be the same hand in frame, same sign of frame.
Yeah, so it's a little, I drew the one which is a little bit harder. Suppose I'd drawn this was red was pointing this way and blue is pointing into the board, and here red is pointing this way and into the board. Then it just goes shoomp.
Well, but I mean, the thing that I'm sort of getting is that if you've got a left-hand plane on the one hand, it should end up with a right-hand plane on the other side.
Yes.
So you couldn't do.
Yeah, so this one is okay, because this does go left to right.
I guess the conclusion I'm running to is that the signs on those arrows actually make it too.
They do. They do. This existing has required d squared equals 0 on my original complex. That's right. So the one-dimensional ones only exist if d squared was 0, and actually if and only if. But even if they exist, they're not quite unique. So that's the framing. So this maybe you could call epsilon, and the framing of each one manifold is, okay, for every a circle has two framings. That's the same as pi 1 stable of S0 or pi 7 of S6. It's this. You're supposed to know this. The circle has there are two ways to frame its normal bundle up to homotopy. Do you know that? Well, ask me later. Trust me. The circle there are two ways to frame its normal bundle. For an interval, there are also two ways to frame its normal bundle once you specify the framing on the boundary. So there are two essentially different ways I could have drawn these arrows. There's not a canonical identification of which is the trivial and which is the non-trivial one for an interval. There is for a circle. One of them extends to the disk and one of them doesn't. But for an interval, there's not a canonical positive and negative. But after we make some global choice, we can nail it down. So I'm not going to tell you the global choice, but the framing of each one manifold is an element of 0 or 1 for each component. Where 0, I'm thinking it's trivially framed, and 1, I'm thinking it's non-trivially framed. But again, that only makes sense for the circles. It doesn't for the intervals. It's a little bit arbitrary for the intervals. Arbitrary global choice for the intervals. So if you wanted square 2, what the extra data you need is you needed signs. So you needed to have the usual differential on a complex. And then you need this framed cancellation rule. You need this framed one-dimensional moduli spaces. And so you're used to lots of places you have one-dimensional moduli spaces, and this is the extra information you needed to choose about them was a framing. So now you can take your favorite Floer theory, or not homology or whatever, and try to find this data, and then it gives you a square 2. Examples. I want to do a bunch of things in the remaining 7 minutes. Maybe I won't do examples. The homework has some examples on it. Just for some very simple flow categories of what the space you get is. What I want to do is tell you the rest of the strategy for computing square 2. So a framed, I'm going to abbreviate, a F1FC is in Smith normal form. If, okay, for every x, there is at most one y such that the zero-dimensional moduli space f of xy or f of yx is non-empty. And if f of xy is non-empty and is zero-dimensional, it consists of p to the k points, all with the same sign. For a non-example, this is not in Smith normal form, because, for example, this B has this space non-empty and also that one non-empty. Also, it has this one non-empty and that one non-empty. I mean, it's got tons of and it's got 4 non-empty ones, so it's only allowed 1 non-empty one. Okay. If you're trying to compute homology of a chain complex, what you do is you put it in Smith normal form. At least that's one good way to do it. And then you can just read off the homology. So this is the analog of a chain complex looking like a bunch of z's plus some z goes by p to the k z. So 2-step complexes and 1-step complexes. This is the first one saying it's 2-step complex or 1-step complex. The second bullet doesn't quite have, I mean, the p says this is a prime power. That's just to make it tidy. If f is in Smith normal form, it's easy to read off square 2. If I look at one of these one-dimensional moduli spaces, M of CA, well, the boundary of it is a disjoint union over B of f of CB times f of BA. But for each B, one of the two of these is empty. Okay, so this is empty. So f of CA is a closed framed one-manifold. And square 2 of A, I don't know why it's written, why there's so many parentheses, is this element of Z mod 2, f of CA times C, plus perhaps other generators. So what this is, again, I said there are two framed one manifolds, so pi 1 stable of S naught. This is some number of circles, some trivially and some non-trivially framed. We count how many non-trivially framed mod 2. Okay, and finally, you can put any flow category in Smith normal form by doing some very simple moves. So there are analogs of the row and column operations you would do for, so there are analogs or lifts of the row and column operations you want to do to flow categories. So for example, the first thing you want to do, well, I don't know, there are lots of ways to simplify this complex. But one of the things you might do first is you might replace, say, B1 by B1 plus B2. And what that does is a column matrix. I didn't write it out with matrices. Well, it does a column operation to this matrix and a row operation to that one. I mean, it turns that complex into C1, C2, B1, B prime, B2, A1, A2. And now the differential of this is 0. The differential of this is not changed. This is minus 1 and 1. And this goes there, and that goes there. So if I make this substitution, I mean, this change of basis, then that changes. And you can carry along the framed one manifolds in the process. It's this sort of simple formulas, though, with a bunch of cases. for carrying along the frame as a one manifold. So you just do that until this complex was reduced to Smith normal form, and then you've computed square 2. I thought I would end with some questions in my remaining minus 50 seconds. Open problems. 1. Find a faster way to compute square 2 on Khovanov homology. This is pretty good, except you have to work with the whole Khovanov complex, whereas the fast way you compute Khovanov homology is by using decomposition into tangles, a sort of divide and conquer strategy. So the question is, find a divided, like, for example, divide and conquer. Okay, 2. Define square 2 on your favorite knot homologies. I gave you a bunch of new concordance invariants last time, but I didn't give you any concordance homomorphisms. So can you get new concordance homomorphisms? From this strategy. And actually, maybe I can give you a strategy for doing that if somebody's interested later, but not on tape. 4. Once you have new invariants, disprove the Poincare, four-dimensional Poincare conjecture, since we said that was a potential application. I think I'll stop there. I'm at time. Thanks very much for listening.